the next thing we're going to do with the second derivative is use it as a tool to find out what kind of critical numbers you have. So we'll go back to our critical numbers, f prime equals 0, f prime equals undefined, while also making sure the function is defined. So that means a vertical asymptote is not considered to be a critical number. But as soon as you create your list of critical numbers, you're not really sure what you have. Relative maxes, relative mins, or flat spots. We're not sure which we have, so we would run the first derivative test, which would tell us. But the second derivative is the most rapid way to know what kind of critical number you have. So I want to demonstrate that, and I'll demonstrate it by just doing it graphically first, and then we'll do a problem. So let's take a look at this graph. Now, if you were to investigate the critical numbers, I think you would find these, right? C1 is here because you've got a nice horizontal tangent line there. C2 is here because there's another nice horizontal tangent line there. And the first derivative test would be to check this out. Increasing here, critical number, switching to decreasing. And maybe in your table you would show increasing and decreasing. You'd say, okay, I know what that is. It's a relative maximum. Here you would see decreasing switch to increasing. Maybe in your table you would show the decreasing and increasing and circle that and say, I know what I have, a relative minimum. But there's a much easier way to do this. And it's called the second derivative test. Take a look at the region over here. Take a look at the concavity throughout the entire region. So if we look here, we would certainly call this a concave up region. And if it is concave up, then the second derivative is supposed to be concave down. If it is concave down, the second derivative is supposed to be negative throughout the entire interval. So it's concave down. Therefore, the second derivative ought to be negative. In fact, the second derivative should still be negative here. I don't care what negative value it is. I just care that it's negative. So if we were to just get our critical numbers and simply feed the critical numbers into the second derivative, and the result came out negative, we should know what kind of critical number we have. So we sample the second derivative at our critical number. And if it turns out that it's negative, what you can say is, I'm in a region of concave down, therefore my critical number must be a relative maximum. You notice it's kind of opposite. It's a negative second derivative, but it's a maximum. So what I would do is, instead of going from here to here, I would take this negative concavity and draw a picture of it. And then I can interpret that to be a relative maximum. Now over here, we're in a region which is definitely concave up. And in fact, the second derivative throughout this region ought to be positive. In fact, it ought to be positive here as well, anywhere we go. So what you do is you find your critical number, C2, so we'll put C1 over there. You sample the second derivative at your critical number and just witness what comes out of it. In this case, it would come out positive, and you would say, all right, positive concavity, let me draw a positive concavity. Now I know where we are, we're really down here, so we must be at a relative minimum. And that's really the second derivative test. Second derivative test is merely sampling your critical number into your second derivative, finding out what you get. Do you get a positive concavity, in which case it's a relative minimum, or do you get a negative concavity, in which case you got to draw the picture to know that would be a relative maximum. So let's do an example working that through. One nice thing, we don't have to build a whole increasing, decreasing, or concavity table. So here's a function. Negative 3x to the 5th power plus 5x cubed. The question would be this. Find the relative extrema. and that means the relative maxes and mins. And let's use the second derivative test to identify what kind of critical numbers we're going to discover here. First of all, find those critical numbers. To find your critical numbers, first of all, you need f prime, which is negative 15 x to the fourth plus 15x squared. And then you want to set f prime equal to 0, and you also want to set f prime, you want to find out when it's undefined. I don't think f prime is ever going to be undefined because it's not even a fraction, no square roots, no division. This isn't going to happen, so we don't really need to do that here. So let's set f prime to 0. I can tell you right away that minus 15 or 15 is not a critical number. In fact, we should be able to factor out the minus 15, and we can factor out an x squared also. So that all comes out, leaving me with an x squared and a minus 1. We can continue to factor like this, right? That's the difference of two squares, so that's how you factor that. And the minus 15 is really not relevant to this problem. All right, critical numbers. You set all of these factors to 0, and we discover that our critical numbers are -1, 0, and +1. All right. Now the question is, which ones are these? Relative maxes, mins, or maybe even a flat spot, not sure. Normally, we would have to use those critical numbers as slicers and slice up the domain and make a table of increasing, decreasing, and run the first derivative test. Underneath, you'd show increasing and decreasing, and you'd say, okay, well, that must be a relative maximum. But actually, we can just use concavity, and we don't need to pick representatives at all. We can simply sample the second derivative right there at the critical numbers. Now, I did say second derivative, right? We need the second derivative in order to learn what these are. So f double prime. Okay, let's go up here. We have f prime sitting right here. So f double prime will be minus 60x cubed plus 30x. So f double prime is this quantity. Now, don't set f double prime to 0 or undefined. That would be you trying to find points of inflection. Instead, what I want you to do is simply sample f double prime at your critical numbers. So I wonder what f double prime is at -1. This is 60 minus 30 is positive 30. Now, what region of concavity are we in when x is -1? We're in a region of positive concavity. Positive concavity means concave up. And we're a critical number, though, so we're sitting right down here. So therefore, at x equals -1, we must be sitting at the site of a relative minimum. Next one. Let's do f double prime at 0. F double prime at 0. Minus 60, 0 cubed, plus 30 times 0 equals 0. Well, I'm glad we came up with that one, because that's not concave anything. And the second derivative test says that this is inconclusive. But we kind of know what happens at f double prime equals 0, don't we? That's probably going to be a point of inflection. And what kind of point of inflection will that be? Certainly not one of these. That switches concave down to up. But 0 is a critical number, and that is not a critical number, so it can't be that. It must be one of these. See, f double prime equals 0 means point of inflection, which means a switch in concavity, which happened. Concave down, concave up. But this is also a critical number. So I think it's this kind of point of inflection that we discovered. However, for the second derivative test, it formally states that when f double prime is 0, we're supposed to say inconclusive, and therefore we rely on the first derivative test to really tell us what's going on. So that one was inconclusive, although I'm pretty certain most times it's a point of inflection. And finally, f double prime of 1. That would be minus 60 times 1 cubed plus 30 times 1. Minus 60 plus 30 is minus 30. This is a region of concave down. Draw concave down so that you know what's going on. Right here at x equals 1, what is this? It's a relative maximum. That's the second derivative test. Second derivative test is for you to find your critical numbers. We don't need to build any tables. And plug in the critical numbers into the second derivative, which says this is the kind of concavity you're in right now. You draw that concavity, and it leads you to the conclusion as to what kind of critical number you have, relative max or relative min. When f double prime ends up being 0, it's safe to infer that you have a point of inflection, but like I said, the formal definition says inconclusive, meaning you can go back to the first derivative test. As always, I like to graph these things, so we want to see if we got it right. So this is minus 3x to the 5th plus 5x cubed. Let's take a look and see what this thing looks like. Pretty much exactly what we thought. At negative 1, right over here on the bottom, we know that was a critical number, hill valley or flat spot. It's a valley. It's a relative minimum. Our second derivative test indicated that it was in a region of concave up. It certainly was. And I drew a concave up picture so that I knew that this was a relative minimum. At x equals 1 over here, we got f double prime to be negative, which indicated a region of concave down, which it is, concave down. And that told me, when I drew the picture, that it is a relative maximum, which shows up on the graph. And finally at 0, when I set f double prime, I didn't set f double prime, I plugged x equals 0 into it, and I got f double prime equals 0. Supposedly inconclusive. However, I think we drew an inference from that it was a point of inflection, and in fact, it was one of these flat points of inflection, and that's precisely what we got. So I encourage you to try the second derivative test instead of the first derivative test, because it's a lot quicker. It's a lot quicker. Once again, find your critical numbers. How do you do that? F prime equals 0. F prime equals undefined. Throw away your vertical asymptotes. Don't call them critical numbers. However, they do need to go into the table of increasing, decreasing as slicers, so you still need them for those, but they're not considered critical numbers. So now collect your critical numbers, throw away the asymptotes. Get your second derivative, plug the critical numbers in to detect what kind of concavity you have, and that should infer what kind of critical number you have, relative maximum or relative minimum, or inconclusive, but really, most times, that's going to be a point of inflection, a flat spot. So it's a nice short video, hopefully, and I'd like you to go off and try some of these homework problems. If you do end up having trouble with them, let me know. Send me an email. That's the second derivative test. Thanks.